Hello everyone. I hope you are doing very well. So today, as you all know, we are going to see the theory part 7 of our chapter Haloalkanes and Haloarenes. So let's begin today's topic, NCERT chapter 6 Haloalkanes and Haloarenes theory part 7, and today we are going to see the section 6.7. This is disclaimer. Objective. So after attending this lecture, you will be able to correlate the structures of haloalkanes with the various type of reactions. Topics that we are going to cover according to the NCERT. Firstly, the section 6.7, that is chemical reactions, and the section 6.7.1, reaction of haloalkanes. And lastly, we will solve an example 6.5. So let's start with our first topic, 6.7, chemical reactions. The chemical reactions of haloalkanes and haloarenes. Haloalkanes and haloarenes both react differently because they are different molecules, right? Haloalkanes you can also say alkyl halide, and haloarenes you can also say aryl halide, right? Haloarene includes the benzene ring, aromatic ring along with the halogen bonded with it, and haloalkanes includes the alkyl group bonding with the halogen. They both react differently. In the haloalkanes, sp3 hybridized carbon atom is bonded to the halogen, right? Because there is no any kind of double bond present. So sp3 hybridized carbon we have in the haloalkanes, which are bonded to the halogens. Meanwhile, in the haloarenes, the carbon is sp2 hybridized that is bonded to the halogen atom. If you see this diagram where this is benzene ring, aromatic ring, and it is bonded to a halogen. Halogen here is bonded to this carbon of a benzene ring, and this carbon is undergoing in the making double bond. So this is a sp2 hybrid carbon. On the other hand, if you see the structure of alkyl halide given here, where halogen is bonded to the carbon, which is actually a sp3 hybrid carbon, right? So in the haloalkanes, sp3 hybridized carbon actually bonded to the halogen, and in the haloarenes, sp2 hybridized carbon bonded to the halogen. 6.7.1, reactions of haloalkanes. So let's see the haloalkanes reactions, how they happen and what are the types, right? What are the reactions they show? Reactions of haloalkanes are divided into three major categories. First, nucleophilic substitution reaction. So haloalkanes show nucleophilic substitution reactions where there is substitution of nucleophiles. Second major category is elimination reaction. So haloalkanes also show elimination reactions where some atom is going to eliminate from the molecule, right? And third major category is reaction with the metals. So haloalkanes also show the reactions with the metals. So let's study in detail the first category, that is nucleophilic substitution reactions shown by haloalkanes. Reaction in which a nucleophile replaces already existing nucleophile in a molecule is called nucleophilic substitution reaction. So a reaction where there is a molecule in which there is already existing nucleophile which is going to be replaced by another nucleophile. That kind of reaction is called nucleophilic substitution reaction. So the nucleophile is undergoing the substitution process. One nucleophile replaces the another in the molecule where there is already existing nucleophile is there, right? So this nucleophilic substitution happening in the reaction, and that reaction is called nucleophilic substitution reaction. Carbon halogen bond, which is having partial charges, that like partial positive on the carbon and partial negative on the halogen due to the polarization of this carbon halogen bond. So carbon halogen bond is susceptible to attack by the nucleophiles that are actually electron rich species. Okay, so carbon halogen bond is susceptible to attack by the nucleophile. So where nucleophile attacks in the haloalkanes? The carbon halogen bond, because halogen here having partial negative charge is going to be replaced by the nucleophile, that means electron rich species, because X, that is the halide ion, is also a nucleophile. Nucleophile attacks the electron deficient carbon. So nucleophile, because it is an electron rich species, it is going to attack on the carbon which is electron deficient, because that electron rich species nucleophile is going to give its electron to the electron deficient carbon. So nucleophile is going to attack on the carbon which is electron deficient, which doesn't have electrons, or you can say which doesn't have enough electrons. Halogen atom leaves as a halide ion as X negative, which is called the leaving group. And after the nucleophile attack on this partial positive carbon, which is electron deficient carbon, this halide ion, this halogen atom, leaves as a halide ion as X negative, and we also call it as leaving group because it is leaving from this carbon halogen bond after the breaking of the carbon halogen bond. So nucleophile, which is electron species, this is going to attack on the alkyl halide, on the specifically carbon halogen bond, on the carbon which is electron deficient, and then the nucleophile going to replace this halide ion, this halide leaving group, and the halide ion is going to leave, and the nucleophile replaces its place, or replaces the place of the halogen present in the alkyl halide and going to bond with the alkyl group, right? So you will get RNU, that means R attaching with nucleophile plus leaving group, that is halide ion, will be out from our reaction. General nucleophilic substitution reactions. So you can see this is the reaction where alkyl halide is reacting with sodium hydroxide, and in the product we are getting ROH, which is an alcohol, and plus sodium halide, right? So this reaction forms alcohol. The product we are getting is alcohol, and this reaction is actually nucleophilic substitution reaction shown by the haloalkanes, right? Haloalkanes is there, halogen and alkane group. It is reacting with the NaOH, sodium hydroxide, where this hydroxide ion is going to replace the halide ion, and you will get an alcohol plus sodium halide as your side product. Second reaction is this reaction, which is also known as Williamson synthesis. It is following SN2 mechanism, where the haloalkanes is reacting with sodium, this NaOR prime. Okay, R prime is different from R group. Okay, that's why we are using R prime, or you can also say R prime may or may not be equal to R, and you are getting an ether, ROR prime plus sodium halide. Okay, so this reaction is giving you an ether, and this reaction is forming an ether. Okay, so in this Williamson synthesis we use the primary alkyl halide for the effective results. Why? Because secondary and especially the tertiary alkyl halide tend to undergo the elimination rather than the substitution, and it leads to alkene as a byproduct instead of the ethers. Okay, so that's why we are using here in this Williamson synthesis we use primary alkyl halide mostly, and both like symmetric and asymmetric, both type of ethers you can obtain from this Williamson synthesis by this method. Okay. Next reaction shown by haloalkanes, which is a nucleophilic substitution reaction, where Rx, that is haloalkanes reaction, reacting with potassium cyanide KCN. Okay, this is ethanolic, or you can say alcoholic potassium cyanide, and it is giving you RCN plus KX. Okay, so you are getting alkyl cyanide, or you can say nitrite, right, as your product. RCN, right? So here also the nucleophilic substitution happening, like CN negative you are having here as a nucleophile which is going to attack on the carbon at which the halogen is bonded, which is electron deficient carbon, and the cyanide negative is going to attach with that carbon and replaces the halogen, and this halide ion is going to be removed and it is going to be attaches with the potassium to form the potassium halide. Okay, so these are some general nucleophilic substitution reactions that the haloalkanes show. Nucleophilic substitution of alkyl halides, that is RX, that is haloalkanes. So if you see, this is a table representing the reagent, nucleophiles, substitution product, and the class of main product. Okay, so if you take the reagent sodium hydroxide or potassium hydroxide, you are going to get the nucleophile from this as OH minus hydroxyl ion, and the substitution product after the reaction with the alkyl group RNU, right? So nucleophile we know, so R, after the addition with R, we are going to get the substitution product as ROH, that is an alcohol. So main class of, or you can say main product class is alcohol group. Okay, similarly for the water molecule, we are going to get the alcohol as your main product, NaOR prime. Okay, the nucleophile you are going to get is R prime O minus, and the substitution product is ROR prime, that is ether. So the class of the product is ether. Sodium iodide, you are going to get the nucleophile as iodide, substitution product as alkyl iodide, and the class is alkyl iodide, right? Now for the ammonia, R prime NH2 and R prime R double prime NH. The substitution product you are going to get will be RNH2, RNH R prime, and RN R prime R double prime. Okay, and the class of main product is going to be primary amine in the case of amine, secondary amine in the case of R prime NH2, and tertiary amine in the case of R prime R double prime NH. Okay, so this table is showing us that how you can get different substitution products and their classes after using different reagents and after getting different nucleophiles from those reagents. So these are the nucleophilic substitution of alkyl halides products. Continuing on the table, we have some more reagents like potassium cyanide, from which the nucleophile you will get is C negative double bond N, and have this lone pair electrons, right? And the substitution product will be RCN. The class of main product is going to be nitrile, or you can say cyanide. Similarly, for silver cyanide, the substitution product you are going to get RNC, that is isocyanide, or isonitrile will be the class. For potassium nitrate and silver nitrate, the substitution product you are going to get is RON double bond O and RNO2 respectively, and the class of main product will be alkyl nitrile and nitroalkane. When the nucleophile is going to attach from the nitrogen atom with the alkyl chain, then the class of main atom will be nitroalkane. When the nucleophile is going to attach with the oxygen atom with the alkyl group, then it is going to call the class is going to be alkyl nitrile. For R prime COOAg reagent, the nucleophile is R prime COO minus, and the substitution product you got is R prime COOR. Okay, so this nucleophile is going to attach with the alkyl group R, and the class of main product you are going to get is ester. Then the reagent is lithium aluminium hydride, which after the substitution, the product you are going to get is an alkane. Okay, so the class of main product is hydrocarbon. Okay, and then the reagent is R prime minus M plus. The nucleophile is R prime minus. The substitution product is R prime minus will going to attach with the R group, and the class of main product will be alkane. Okay, so these are the reagents and their classes of main products that they are going to give. after the nucleophilic substitution of haloalkanes. Let's see what is ambident nucleophiles. Nucleophiles attack through two different sites. Okay, so ambidented nucleophiles are corresponding to those nucleophiles which can attack through two different sites. That means they have two different atoms present in it, which can bond with the carbon. Okay. For example, we have cyanide, that is Cn negative, and NO2 minus. Okay, we have these two nucleophiles which are actually ambidented nucleophiles. How? Let's see one by one. Let's first of all cover the cyanide, Cn negative. Cyanide negative have two positions available for the attack with the carbon. That is, first of all, the carbon present in the cyanide, and second is nitrogen present in the cyanide. So carbon can also bond with the carbon present in the alkyl group, and also nitrogen can also form the bond with the alkyl group, right? So two positions are available in the cyanide nucleophile for the attack on the carbon, that is carbon or nitrogen. Now in the covalent bonding, the nitrogen lone pairs is more available, so attack will be from the nitrogen. Okay, so those nitrogen lone pair is going to be bonded or is going to be participate in the sharing of electrons with the alkyl group to form the bond, and the attack will be from the nitrogen atom from the of the cyanide nucleophile, right, and form the covalent bonding. Similarly, in the ionic form, carbon atom bears negative charge, okay, and due to that, the attack will be this time now from carbon, and carbon-carbon bond will form. Okay, so if you see the cyanide ion, it can be existed in two pairs or in two structures form. First of all is C negative triple bond nitrogen, and you can also say C double bond N negative or C positive double bond N negative, right? So through carbon, when the linkage is forming, they will form alkyl cyanide, and when linkage is forming through nitrogen with the carbon of the alkyl group, then they are going to form isocyanides. Okay, so negative charge which is localized on the carbon, that is going to result in the carbon-carbon bond which is formed with the substrate alkyl group, and it is stronger than the carbon-nitrogen bond. Okay, so we will prefer in the haloalkanes the carbon-carbon bond more than the carbon-nitrogen bond. Second nucleophile is NO2 minus, that is nitrite. This is also an ambident nucleophile because two positions are available in this also for the attack. That is, first is nitrogen and second is the oxygen atom which is present in the nitrite, nucleophile. Now, in the ionic form, so oxygen will bear a negative charge, so attack will be going to happen from the oxygen atom. Okay, so NO2 you can write it as O negative single bond N is having lone pairs and is making double bond with the oxygen, the other oxygen. Okay, so O negative single bond N, one lone pair, double bond O. Okay, so two position available for attack, nitrogen and oxygen, and in the ionic form the oxygen will be having negative charge and the attack will be going to happen from the oxygen to the carbon, and in the covalent bonding the nitrogen lone pair going to attack on the carbon and the attack will be happen from the nitrogen. Okay, so when the attack or when the bonding is forming between the carbon of alkyl group and the oxygen of the nitrite nucleophile, then alkyl nitriles will be formed, and when the linkage is happening between the nitrogen atom of this nitrite nucleophile and the carbon atom of the alkyl group, then the nitroalkanes will be formed. So these are the examples of ambident nucleophiles that are containing two different sites to attack through to the carbon of the alkyl group. Let's talk about again the nucleophilic substitution reaction. So nucleophilic substitution reaction is again of two types. First is substitution nucleophilic unimolecular. We also commonly called it as SN1 reaction. Okay, so the full form is substitution nucleophilic unimolecular. And the second type is substitution nucleophilic bimolecular, that is SN2. How can you represent the nucleophilic substitution reaction? So the representation is SNX. Okay, S where is the representation for substitution, N is the representation for nucleophilic, and X is the substitution for the order of the reaction. Either the reaction will be first order or the second order. So substitution nucleophilic unimolecular means first order reaction, and the substitution nucleophilic bimolecular where X will be 2, that means the second order reaction. Let's see the substitution nucleophilic unimolecular reaction, that is SN1 reaction. So SN1 is again a two-step reaction. Okay, so SN1 reactions happens in a two-step process. The mechanism involves two steps. So step 1 is actually a slow step, and it is also a reversible step. Ionization of alkyl halide to form a carbocation intermediate, which is C positive, and halide ion, that is X negative. Okay, first of all, what will happen? The ionization of alkyl halide, that is haloalkanes, is going to happen, so that we will get a carbocation, which is carbocation intermediate, which is containing C positive carbon, and a halide ion, that is X negative. Okay, so for example, let's take this tertiary butyl bromide. The bromine is their halogen attaching with this carbon, and this carbon is attaching with the other 3 methyl groups, the other 3 carbons. So step 1 is a slow step, and it includes the formation of carbocation after the removal of halide ion from it, and also you will get the halide ion along with the carbocation. So you can see you are getting tertiary butyl carbocation where the central carbon is having positive charge on it, which is attaching with other 3 methyl groups, and also you get a bromide ion, a halide ion. Okay, so if I will tell you the now what will going to happen, the nucleophile, because this is a nucleophilic substitution reaction, the nucleophile is going to attack on this carbocation, right? Okay, so this is step 1 because it is a slow step, it is a rate determining step. Okay, so rate determining step, how? Because the rate here is actually depend upon the alkyl halide concentration. Okay, the step 2 is a fast step, which includes the nucleophile attacks on the planar carbocation. So you got your carbocation in your previous step. Now the nucleophile is going to attack on this carbocation, which is your step 2, and it is a fast step. Then after the attack of this nucleophile on the carbocation from both the sides, from either of the sides, often result in the mixture of stereoisomers. So sometimes what happen, because the attack of nucleophile can be happen from both the sides, it often result in the mixture of stereoisomers. Okay, here you are getting, after the attack of the hydroxyl ion nucleophile attack on this carbocation, you are getting tertiary butyl alcohol, that is CH3 whole thrice COH. Okay, so at this tertiary carbon, the hydroxyl group is going to be attached. So the SN1 reaction is a two-step reaction. Step 1 includes the formation of carbocation intermediate and the removal of halide ion. This is a slow step, and it is a rate determining step. Rate depends on the concentration of alkyl halide only. The step 2 is a fast step, which includes a nucleophile attack on the planar carbocation, and you will get your final product. Okay. Typically, this reaction occurs in polar protic solvents like water, alcohol, acetic acid. Okay, so in this reaction, we use polar protic solvents like water and alcohol. Why? Because the reason is that polar protic solvents stabilize the intermediate and the leaving group. Okay, so this polar protic solvents is actually because this polar protic solvent have molecules with high polarized hydrogen atoms of water, right? So these solvents will surround and stabilize the positive charge of the carbocation via solvation and hydrogen bonding, and also lowering the energy, making its formation easier. For example, if you see this diagram, this carbocation will just form, okay? This carbocation will just form after the first step of the reaction, and the solvent we are using is polar protic. So this water molecules are going to arrange themselves around this carbocation, okay, to stabilize the positive charge of the carbocation, okay, and these water molecules have highly polarized hydrogen atom. So these solvent molecules are surrounded and stabilizing the positive carbocation via the solvation and hydrogen bonding, lowering its energy and making the formation of the product easier. Okay. Also, the polar protic solvent stabilize the negative charge by living group, okay, of the living group. So negative charge of living group is also stabilized by the polar protic solvent by hydrogen bonding, and it will facilitate the departure of living group from the solution more easily. Okay, so this is what is happening, and this is the reason behind the use of polar protic solvents typically while in this reactions, which is substitution nucleophilic unimolecular reactions. So as we see that the substitution nucleophilic unimolecular reactions happens in the two step. The first step is alkyl halide forming carbocation, and the living group or the halide ion is left from the reaction. This is a slow step, and this is a rate determining step. Rate is dependent upon this alkyl halide concentration. The second step involves the fast step, which is the carbocation and the nucleophile reaction, where nucleophile attacks on the carbocation from the both sides and form your final product. Okay, RNU, right? Kinetics. Reaction rate depends on slowest step. So your reaction rate is actually depending upon the slowest step, because that's what chemical kinetics do, right? If you study in the chemical kinetics, the reaction rate is depending upon the slowest step of the reaction, the overall reaction. Okay, so slowest step is your first step. So the slowest step, that is the rate determining step, includes only the concentration of alkyl halide, right? So remember, while writing the rate law, we consider the concentration of your reactant. Here in the step 1, which is the slowest step, the reactant is only alkyl halide. So we only include the rate or include the concentration of alkyl halide into the rate. So rate will be equals to K times the rate constant multiplied by the concentration of alkyl halide, that is Rx. So this is a first order reaction, right? That the reaction that you can see that rate expression, right? Rate is K times Rx. So here the concentration of alkyl halide are having power 1, right? So it is a first order reaction. Okay, it is only depending upon the concentration of the reactant, that is alkyl halide, present in the slowest step, that is step 1. Reactivity order. Now let's talk about the reactivity order on the basis of the carbocation. So stability of carbocation is the key factor, right? Because the carbocation here is playing a major role, because this is a two-step reaction. First is involving the formation of carbocation. So if you know the order of stability of carbocation, then you can consider that order will be also going to depend upon the reactivity is also going to be depend upon the stability order of the carbocation, right? So the stability of carbocation is the tertiary carbocations are very, very stable, then the secondary carbocation, then primary carbocations, and then comes the methyl group, simple CH4. So the order of reactivity will also be similar, that tertiary carbocation will have the highest reactivity order, then the secondary carbocation, then the primary carbocation, and then comes the methyl group, right? So the carbocation stability or you can say order of reactivity will be the similar to the order of stability of carbocation, because in the first step of this substitution nucleophilic unimolecular reaction, there involves the formation of carbocation. So if you are forming a stable carbocation, that means the rate will be higher, the reactivity will be improved if you are forming a tertiary carbocation compared to the primary carbocation, right? So the rate or the order of the reactivity and the stability of carbocation are similar in the SN1 reaction, and this is actually the key factor. Also in the allylic and benzylic halides. Allylic means the halides where the halogen is attaching with the carbon which is present in the double bond chain. And benzylic halide means halogen is attaching with the benzene group. Okay, benzene chain or benzene ring. So allylic and benzylic halides, they show high reactivity towards the SN1 reaction. So they generally show the nucleophilic substitution by following the SN1 mechanism. Why? What is the reason? That carbocations are resonance stabilized in these. In the allylic and in the benzylic halides, the carbocations that are forming in the first step, they are resonance stabilized. So charge will be going to be stable as per the resonance. If you see the allylic carbon, where this is CH2 double bond CH, single bond CH2 positive. Okay, so after the removal of halogen, there comes a positive charge on the carbon, and this is a carbocation. Now, this positive charge can be stabilized by the resonance shown by this allylic carbon. So, this double bond, the sharing electrons here, or the charge here is going to go on this carbon to stabilize this positive charge, and this positive charge is going to come on this carbon, this double bonded carbon. Okay, so this structure can be also written as this structure after the charge stabilization by resonance. Similarly, in the benzylic halides, you can see this is a benzene ring attaching with CH2. Okay, and CH2 is attaching with the halogen. After the halogen removal, the halide ion removal, there comes a positive charge on this carbon, right? Now, this positive charge is going to be stabilized by the resonance shown by this benzene ring. Okay, so what will happen? This double bonded carbon, this double bond electron charges is going to be donated to this bond here between the carbon benzene carbon and the CH2 carbon. Okay, so here comes a double bond. Now this double bond is removed from the benzene ring. So here comes a positive charge on the carbon from which the double bond charges or the double bond electrons has been removed. So positive charge will be here. Now the other carbon double bond which is present in the ring, now it becomes his responsibility to stabilize this positive charge. So this double bond, or you can say this sharing electrons, is going to go to this carbon to stabilize the positive charge, and because they are going here, the double bond shifted from here to here, and the positive charge will also shifted from this carbon to this carbon because this carbon has donated its sharing electrons to this positive charge carbon, right? So positive charge comes here and double bond comes here. Now the next double bond, it's its responsibility that to stabilize this positive charge present on the carbon. So this double bond carbon or this double bond sharing electrons is going to go on this carbon to stabilize the positive charge, and the double bond will shift from here to here, and the positive charge will go from this carbon to this carbon. Okay, now again the next double bond, which is here, this is going to stabilize this positive charge after making the double bond here, and this positive charge is going to go at this carbon. So the structure that will come after this last structure will be this, the same structure which is present at the first position. Okay, so the charge is stabilized by the resonance. So carbocation is actually resonance stabilized both in the allylic and the benzylic halides. That's why both allylic and the benzylic halides show high reactivity towards the SN1, or you can say they do nucleophilic substitution reaction by following the SN1 mechanism. Now, let's see the next type of substitution reaction, that is substitution nucleophilic biomolecular, that is SN2. Now, this reaction, that is SN2 reaction, is a single step reaction. It doesn't involve two step. It is only a single step reaction. No intermediate form, because it is a single step reaction. So, in this reaction, there is not any involvement of intermediate formation. Incoming nucleophile interacts with the alkyl halide and break the carbon halide bond, and new bond formed between attacking nucleophile and carbon. Okay, what will happen here? The nucleophile, here also the nucleophile is going to substitute the already existing nucleophile, right? So what will happen? The incoming nucleophile interacts with the alkyl halide, the carbon halogen bond, and break the carbon halogen bond, and new bond will be formed between the attacking nucleophile and the carbon of carbon halogen bond. So you can see the nucleophile will going to attack on the carbon halogen bond, okay, due to which the carbon halogen bond will start to break down and the nucleophile carbon bond will start to form. So this you can say the state comes here where there is the carbon at which 3 hydrogen are there, and also hydroxyl group and chlorine group both are present. So chlorine and the carbon bond is breaking, and hydroxyl group and carbon bond is, or you can say oxygen and carbon bond is forming. Okay, then what will happen finally, that this carbon halogen bond will break and this oxygen carbon bond will form, and you will get your final product as your alcohol. Okay, plus chloride, that is leaving group, will be leave from your reaction. So what is the mechanism of SN2? So nucleophile attacks the carbon atom from the side which is opposite to the side of the leaving group. So at the side at which leaving group is present, the nucleophile attacks from the opposite side of that. Okay, so that here the backside attack is happening in the mechanism of the SN2 reaction. Okay, so nucleophile attacks on this carbon from the back side. Okay, from the opposite side of the side at which the halide is already present, which is bonded with the carbon. So this is the reaction for SN2 as we have seen. So let's talk about the transition state, that is this state which we have enclosed in this square bracket. So this transition state is formed where carbon is simultaneously bonded to both the incoming nucleophile and the outgoing leaving group. So in the transition state, what is happening? The carbon is simultaneously bonded to the incoming nucleophile, which is here hydroxyl group, and the leaving group, that is here is chloride ion. Okay, so carbon is bonded with both the ions, the incoming nucleophile and the leaving group. So in the transition state, all the carbon hydrogen bonds, so carbon is attaching with 3 other hydrogens, right? Basically, it is forming 5 bonds in the transition state, in which one is forming and other one is breaking. Other than that, there are 3 permanent bonds which it is forming with the hydrogen atoms. So all these carbon hydrogen bonds, they are in the same plane. Okay, so what will happen, that after this transition state is attained by this molecule where the carbon is having 5 bonds, in which one bond is between the oxygen and the carbon which is making, and one bond is between the carbon and chlorine which is breaking, and another are the bonds which are present between the carbon and hydrogen. So in this process, in this transition state, what will happen, that these all 3 carbon hydrogen bonds came in same plane, and the living nucleophile and the attacking nucleophile, they both are partially attached to the carbon. Okay, as I said. So in the transition state, what happens, that all 3 carbon hydrogen bonds come in the same plane, and the nucleophile and the chlorophyll. Okay, nucleophile that is incoming, and the living group, which is also a nucleophile, so you can call it as living nucleophile. So attacking nucleophile and living nucleophile, they both are partially attached to carbon. Okay. Now, in the transition state, carbon is simultaneously bonded to the 5 atoms at the same time. Lone pairs of the nucleophile, that is here hydroxyl ion, attacks the partial positive carbon of carbon-halogen bond. Okay. Now, what will happen? That more efficiently, the lone pair of nucleophile of hydroxyl group. Okay. So, nucleophile here is hydroxyl group. So, hydroxyl group, that is our nucleophile. Its lone pair attacks on the partial positive carbon, which is present in our molecule, which is forming the bond with the carbon, which is forming the bond with the halogen. Okay. So, lone pair of nucleophile attacks on the carbon of carbon-halogen bond. So, carbon-halogen bonds begin to break with the electron pair moving on to the halogen. Because it is a halogen, it has electronegativity. So, halogen will remove, or halogen will starts to break the bond with the carbon. Okay, so carbon-halogen bond starts to or begins to break with the electron pair going towards the halogen. Now, SN2 reaction can be represented diagrammatically as shown. Okay, so if you form the diagram of the SN2, the first one is this, which we have seen, that hydroxyl ion, which is our nucleophile, is attacking on the carbon from the opposite side of the carbon-halogen bond, and there comes a transition state where the carbon is simultaneously bonded to 5 atoms, where the attacking nucleophile and the leaving nucleophile both are bonded partially with the carbon, right? The lone pair present on our nucleophile attacks on the carbon-halogen bond carbon, and then the halogen carbon bond starts to break, and the shared electrons will going to move onto the halogen. Okay, so this bond breaks and you will finally get your product, which is here alcohol, like methyl alcohol plus chloride, which is our living group, so it will be left. Okay, so this is a single step reaction happening in only one step. The other way is this, which is figure 6.2. This is the representation for the hydroxide ion. Okay, where this red one is representing the red ball is representing the incoming hydroxide ion. Okay, so this brown ball is representing the carbon, and this big green ball is representing the outgoing halide ion, right? So this hydroxide is going to attack on the carbon from the opposite side of the carbon chloride or carbon halide bond. Okay, so this is going to attack on this molecule where the carbon halogen bond is already existing. So this will attack from the opposite side of carbon from the side of the carbon halogen bond. And then this transition state will be occur where there is the partially bond of carbon hydroxide and carbon halide is present. Okay, and all the other carbon hydrogen 3 bonds comes in the same plane, and the lone pair present on our hydroxide is going to attack on the partial positive carbon of carbon halogen, and the carbon halogen bond will going to be break down, and you will get this final product where hydroxide ion is going to be attack or is going to bond with your carbocation, and the halide ion will going to be removed from the process or removed from the reaction. Okay, so this is the 2 ways, or you can say 2 diagrams through which you can represent the SN2 reaction, how it is happening in a single step. So what we have seen that it is the reaction which is happening in the single step. So alkyl halide, on which nucleophile attacks from the opposite side of the carbon halogen bond, and then you will get your final product where nucleophile is finally bonded with the alkyl group and the halide group will be left from the reaction. Kinetics. So kinetic is that reaction rate depends upon the concentration of both alkyl halide and nucleophile. Here in this SN2 reaction, the reaction rate is depending upon the concentration of alkyl halide and nucleophile both. So The reaction rate, if you write, it will be K times rate constant times Rx. That is your alkyl halide concentration multiplied by nucleophile concentration. So the order of the reaction will be second. So it is a second order reaction. Okay, 1 plus 1, 2. So it is a second order reaction and it is a single step reaction. It is a second order reaction. Rate of reaction is depending upon both concentration of alkyl halide and nucleophile. Reactivity order, if you talk about the reactivity order of SN2 reaction. So presence of bulky substituents on or near the carbon atom hinders the attack of nucleophile. Because in this reaction, there is not any formation of carbocation is happening, right? So that means in this reaction, the SN2, the reactivity is not depending upon the carbocation stability, right? In the other way, you can say that if there is any bulky substituent is present on the carbon atom, which is going to be carbocation, or near the carbocation carbon atom, that group will going to hinder the attack of nucleophile. Because in a single step, the nucleophile is going to attack on the carbon from the opposite side of carbon halogen bond, right? So to proper attack or for proper bonding, there should not be present any kind of bulky substituents near or on the carbon atom. So steric hindrance is the key factor here. The order of reactivity will be the opposite from the SN1. That methyl halide is going to be highest reactive, then primary halide, then secondary alkyl halide, then tertiary alkyl halide. Okay, we will understand how. So you can also write in this way that CH3X will be having highest reactivity order, then CH3 CH2X, then CH3 whole twice CHX, which is secondary alkyl halide, and then least reactivity will be for CH3 whole thrice CX, which is tertiary alkyl halide. So tertiary halides are least reactive because they are in the tertiary alkyl halides. At the carbocation carbon, there is a presence of bulky substituents which hinders the attack of the nucleophile. So that's why steric hindrance will be going to be there, due to which the nucleophile can't properly attack on the carbon to form the bond with it. So tertiary halide reactivity will be least. Steric effect in the SN2 reaction. If you look upon this diagram, which is figure 6.3, steric effects in the SN2 reaction, the relative rate of SN2 reaction is given in the parenthesis. So you can see this is your methyl, okay, where this is methyl halide, okay, CH3X. Now nucleophile is going to attack from the opposite side of carbon halogen bond, and it can easily attack because only small hydrogen atoms are bonded with the carbon. So the relative rate is 30. If you see here where the carbon halogen bond, okay, so carbon which is also bonding with halogen, it is having one substituent as bulky substituent as methyl group, right? So on this carbon we have CH3 and 2 hydrogens. So due to the presence of one bulky group on this carbon, the nucleophile will affect or will the nucleophile attack will be affected, and the nucleophile will experience the steric hindrance in attacking this carbocation or this carbon, right? So this is basically ethyl chain, okay, basically this is ethyl because 2 carbons are there in this structure. So this is primary ethyl, and the relative rate due to the presence of this bulky group, the relative rate is 1, which is very, very less from the methyl halide. Now, if you take isopropyl, now if you add more bulky groups to the carbon, you add 2 methyl groups, okay, along with 1 hydrogen group. So due to the presence of now 2 bulky substituents, the nucleophile attack will affect more, okay. So this is isopropyl secondary, or you can say secondary isopropyl, and the relative rate will very, very decrease from 1 to 0.02. And in the last process, if you see a tertiary butyl, which is actually tertiary. Okay, that means the carbon is attaching with other 3 carbons, because 3 methyl groups are present in this on this carbon. Okay, so nucleophile can't effectively attack on this carbon for making the bond with it from the opposite side of carbon halogen bond. So the relative rate is 0. So this diagram is showing that the order of reactivity will be highest for methyl halides and least for tertiary halides. Okay, so due to the presence of these bulky substituents on the carbon, they will hinder the attack of the nucleophile on the carbon, and steric hindrance will be the factor that are going to affect this bonding between nucleophile and the carbon. So the relative rate will be affected. So methyl halide will be having the highest reactivity for this substitution nucleophilic biomolecular. Okay, let's solve an example. Example 6.5. The example is haloalkanes react with the potassium cyanide to form alkyl cyanides as your main product, while silver cyanide forms isocyanides as the chief product. Explain. So the example asking is that haloalkanes, when you react them with the potassium cyanide, they form alkyl cyanide, but when you use silver cyanide with the haloalkanes, they will form isocyanides. Why this is happening? Okay, so you have to tell or you have to explain it. So you have given some time. Try to analyze this question, and then we will see the correct explanation. Okay, let's see. So for this example, KCN. First, we will talk about KCN, potassium cyanide. Now, this potassium cyanide is ionic. Okay. Ionic means when you dissociate the potassium cyanide, it will dissociate in the solution and release the cyanide ion and the potassium ion. Right? K positive and Cn negative you will be getting from the potassium cyanide when you dissociate it into the solution. So, because cyanide, that is Cn negative, is an ambident nucleophile. That means this cyanide ion is having this ability to attack or to have different sites through which it can attack to the substrate, that is the alkyl group, right? So it can attack from both the carbon and the nitrogen atom because it is an ambident nucleophile. So carbon-carbon bond is stronger comparative to carbon-nitrogen bond. So the carbon will donate its electron pairs on the haloalkanes and form alkyl cyanide. Okay, because it can bind through carbon-nitrogen both. Cyanide can bind through carbon and nitrogen both. So and the carbon-carbon bond is stronger compared to carbon-nitrogen bond. So carbon will form the bond with the substrate, and the electron pair of the carbon will be donated to the haloalkanes, and they will form the main product as the major product as the alkyl cyanides after the reaction of haloalkanes and potassium cyanide. Now, if you talk about the silver cyanide is a covalent compound, forms by sharing of electrons. So it does not dissociate to give the cyanide ions in the solution, right? Because it is covalent, when you dissociate it into the solution, it will not give you cyanide ions, due to which due to this non-dissociation of silver cyanide nature into ions, this results in the donation of nitrogen lone pair to form the isocyanide, as carbon is not free to attack to form the alkyl cyanide. Okay, so in the silver cyanide case, because we can't get the cyanide ions after the dissociation of the silver cyanide because of its covalent nature, what will happen? The nitrogen lone pair is going to be form the bond with the substrate, with the alkyl group, okay, with the carbon, and you will get a isocyanide as your major product. Okay, and in this silver cyanide, the carbon is not free to attack to the carbon to form alkyl cyanide. So that's why nitrogen lone pair is going to attack on the carbon of the alkyl group and form and give you isocyanide as the major product. Okay, so this is the main reason that why when you react the haloalkanes with potassium cyanide, you are getting alkyl cyanide as your major product after the carbon-carbon bond. But when you are using silver cyanide at place of potassium cyanide, you are getting isocyanides as your major product. Okay, let's see the summary. So we have covered the ambident nucleophiles, the nucleophiles that can attack from both the sides, or that have two sides to attack from. For example, cyanide ligand and NO2 ligand. Nucleophile or nucleophilic substitution reaction, where the substitution of nucleophiles happens. So replacement of existing nucleophile by the another incoming nucleophile is known as nucleophilic substitution reaction. That is what happening in the nucleophilic substitution reaction. There are two types of nucleophilic substitution reaction. Major two types, which is nucleophilic substitution unimolecular. You can also say it as SN1, whose reaction of rate is first order. And there is nucleophilic substitution biomolecular, that is SN2, whose reaction of rate of reaction is second order. So if we talk about the nucleophilic substitution unimolecular, we have seen that it is a two-step reaction, and the step 1 includes the intermediate carbocation formation, and the living group will be removed from the reaction. And you can see this example where bromine is attached with tertiary carbon and you are forming a tertiary carbocation plus bromide, which is a living group, is left from the reaction. The step 2 involves the attack of nucleophile on the carbocation formed. So the carbocation you have obtained, the nucleophile is attack on that carbocation and give you a final product, which is here a alcohol. The formation of intermediate is a rate determining step because it is a slowest step. So the rate is going to depend upon the concentration of alkyl halide only. So rate, you can write it as rate constant multiplied by the concentration of alkyl halide. It mostly occurs in the polar protic solvent, which is like water, alcohol and acetic acid, due to the stabilization it provides to the carbocation. And the order of reaction, if you see, tertiary halides are like highly reactive towards the nucleophilic substitution unimolecular, that is a SN1 reaction, and then comes the secondary halide, and then primary halide and the methyl. Then comes the methyl. And this is due to the fact that tertiary carbocation, which is we are getting in the first step, is the most stable. So the tertiary halide will show the highest reaction or reactivity. Then we have talked about the nucleophilic substitution biomolecular, right? Which is a single step reaction, and it is not involving any kind of intermediate formation, and it involves the transition state formation where the carbon is simultaneously bonded to 5 atoms, which includes 3 permanent carbon hydrogen bonds, and 1 is incoming nucleophile and carbon bond, and 1 is living nucleophile and carbon bond. And the rate of this reaction is depending upon the concentration of alkyl halide and the nucleophile both. It is a second order reaction. The order of reactivity for SN2 reaction is highest for methyl halide, then for primary, halide, then for secondary halide, and then for tertiary halide. Because in this, we prevent the attachment or attaching of any kind of bulky groups to on the carbon or near the carbon at which the incoming nucleophile is going to attack. Because if there is any bulky group, the incoming nucleophile will face the steric hindrance, which will going to affect the bonding of nucleophile and the carbon. So the order of reactivity will be methyl halide, which contains the hydrogen bond present around the carbon. So it will be more reactive, then the primary halide, then secondary halide, and then the least reactive will be tertiary halide. Okay. Okay. Thank you so much. That's all for today's chemistry session. Thank you.